Today we are going to see products and quotients in exponential form. Say you take two real numbers theta 1 and theta 2 and then consider the product of exponent of I theta 1 and exponent of I theta 2. By definition, this is cos theta 1 plus I sin theta 1 and this one is cos theta 2 plus I sin theta 2. Let's now calculate this product. So you recall the definition of multiplication of two complex numbers. Real part times real part minus imaginary part times imaginary part plus I times imaginary part times real part plus the other product imaginary part times real part, this one. And then using your simple trigonometric addition formula for sine and cosine, you clearly see that this is cosine of theta 1 plus theta 2, whereas this one is sine of theta 1 plus theta 2. So again it's another number of that form, and this is the exponent of I times theta 1 plus theta 2. So this gives you an idea of why this number has been represented using this notation. It is as if we are having one of the laws of exponents. Isn't it surprising that although these numbers don't seem to have anything to do with exponents, but ultimately when you multiply them, they behave like exponential function, real exponential function. So this means that if you have two non-zero complex numbers z1 and z2 and say their exponential forms are these respectively, z1 is r1 e to the power I theta 1 and z2 is r2 e to the power I theta 2, where of course you understand that these are the moduli of z1 and z2 respectively, whereas theta 1 is an argument of z1 and theta 2 is an argument of z2. Then if you take their product, then the product will be this r1 r2 times e to the power I theta 1 times e to the power I theta 2, which however is this, as we have shown just now. Now from this, what do you get? This argument of z1 z2 equals argument of z1 plus argument of z2, and that we get from this equation. Theta 1 is an argument of z1, theta 2 is an argument of z2. So this is an element in this set, this one is an element in this set, and their sum is an element in this set. You have to properly interpret this equation. These are not single numbers, okay, as you already know. They are sets of numbers. So then what should be the interpretation? The interpretation is this: if any two of these three quantities are given, then there exists a value of the third quantity for which this equation is true. For example, theta 1 is an element of this set, theta 2 belongs to this set. So there exists an element in this set for which this equation is true, and that element is theta 1 plus theta 2. In that sense, for example, say you are given an argument of z1, z2 and an argument of z1, then there exists an argument of z2 for which this equation is true. This equation is important because it helps you find arguments of products very easily. Similarly, instead of product, if we consider quotient of say z1 and z2, then use their exponential form, then we get this. Actually here we multiplied and divided by e to the power I times minus theta 2 to simplify our calculation. Note that we can do this because this type of numbers are not zero. In fact, they are complex numbers of modulus 1. But anyway, from what we saw just now, this will be e to the power I times theta 1 plus minus theta 2, that is theta 1 minus theta 2. Similarly, this one in the denominator will be e to the power I0. This one is 1, but why is it 1? It's not 1 simply because it's e to the power 0. Actually, this is not e to the power in the sense of real analysis, okay. This is cos 0 plus I sin 0. Sin 0 is 0, cos 0 is 1. That is why this is 1. So we now have this. And from this we are going to similarly get another such equation. And that equation of course is this. Argument of this equals argument of z1 minus argument of z2. And here also you have to apply that same interpretation. That is, if two elements of two of these three sets are given, then there exists an element of the third set for which this equation is true. So let's take an example where z1 is minus 1 and z2 is I. Instead of taking arbitrary arguments of these complex numbers, the authors have chosen to take principal arguments. Okay, because why not? The principal argument of minus 1 is pi because it's a negative real number, and the principal argument of I is pi divided by 2 because this. So if you add them up, then by what we saw just now, not this one, the previous one, the sum would be an argument of z1, z2, and the sum is 3 pi divided by 2, and z1, z2 is minus I. So 3 pi over 2 is an argument of minus I, not the principal argument because this has exceeded pi. But from this you can find the principal argument if you tweak this value a little. Because this is one argument and any two arguments of a complex number differ by an integer multiple of 2 pi. So this and the principal argument of minus I, whatever it is, should also differ by some integer multiple of 2 pi. And it turns out that if you subtract 2 pi from this value, then you get minus pi divided by 2 because 3 pi minus 4 pi. And that is nothing but the argument of minus I because minus I is here. So minus pi divided by 2. Now in this example, it obviously looks as if we are not getting much out of this formula because the numbers are quite simple and their product is simple. So instead of doing all these things, you can just simply multiply minus 1 and I. You are getting minus I, from which you can just simply find the argument of the product the usual way. But it won't always be so simple. Sometimes this formula will save much time. And we are going to see another example of this type, where instead of product, we are going to see a quotient of two complex numbers, which won't be so easy. You consider this next example, where the complex number is minus 2 divided by 1 plus root 3i. From the look of it, you can immediately see that trying to first turn this into standard form and then finding argument is much effort. I mean, you have to spend some time to do that. Instead, what we are now going to do is we will find an argument for this and one for this and take their difference. That by that second formula will be an argument of this quotient. So we write like this: since the principal argument of minus 2 is pi and that of 1 plus root 3i is pi divided by 3. So by that second formula, the argument of z will have this value as an element in it, pi minus pi divided by 3. The argument of this minus the argument of this. I say the argument because we are using principal argument. But actually you can use any arguments, okay? Not necessarily these values have to be used. You can use any arguments of these two complex numbers. But anyway, so this will be an argument of z. Do you see how easily we found, and we did not have to first turn this into standard form. We don't have to do those things. And luckily, this actually satisfies those inequalities. So that's why this value is nothing but the principal argument of our z. Next we claim something about powers of complex numbers. Say you have a non-zero complex number z here expressed in exponential form r times e to the power I theta, where of course you understand that this is the modulus and theta is an argument of z. Okay, and say you also have a positive integer n. Then the nth power of z equals the nth power of r times e to the power I times n theta. This is our claim. Let's now establish this claim by induction, of course. The claim of course is obvious when n is 1, because if n is 1 then this claim just reduces to the original given thing. So that's the basis for our induction, and then we make the induction hypothesis. Let the claim be true for some positive integer n. So now next we consider the n plus 1th power of z, which by the definition of such powers is the nth power of z times z. This by the induction hypothesis is this, and z of course is r times e to the power I theta. Then you multiply this to r to the power n and r and get this n plus 1th power of r times this, which from our very first thing today equals this, which however is just this. So that means the n plus 1th power of z is this, which is the claim if we have n plus 1 in place of n. So this completes the induction and establishes our claim. But now we are going to see that this is true not just for positive integers n, but actually any integer, for 0 and negatives as well. For n equal to 0 also the claim is true, because both sides become equal to 1. This side of course is 1 by definition of integral powers. Here also on this side, this 0th power of r is 1, and this is what? This is cos 0 plus I sin 0, that is also 1. And finally we assume that n is negative, n is a negative integer. Then by one of the rules of exponents, which is there for the complex number system as well, just like we have it for the real number system, the nth power of z is z to the power minus 1 to the power minus n. This however is just the multiplicative inverse of z, and then in place of z we write what it is, r times e to the power I theta. Now in the next step we did not actually show it fully, but you can understand what we did. We multiplied and divided by e to the power I times minus theta, so that this part becomes just r in the denominator. So you have 1 divided by r times this. Now this is again a complex number in exponential form, whose modulus is 1 divided by r and minus theta is an argument. But now you see the exponent outside is a positive integer, because original n is negative. So by what you proved just now by induction, you can write this. The minus n goes over the modulus as well as it gets multiplied with this argument. And when you simplify things, ultimately you get the original thing back, even in this case where n is a negative integer. And from this you can derive a consequence which has its own importance. This. Say you consider the nth power of cos theta plus I sin theta, in other words the nth power of our e to the power I theta, where n is any integer. Okay, I am reiterating that n is not necessarily positive, n can be 0, n can be negative, n can be any integer. Then by that rule, this is equal to e to the power I times n theta, which when you write what it is, it looks like this: cosine of n theta plus I times sine of n theta. And this is your familiar de Moivre's formula. And we are going to now end this section with this final example. I forgot to write the example number. Okay, so let's just treat it as an example, something. You will find it in the book. Say we want to find the 7th power of square root of 3 plus I. So if you start doing multiplications, you can imagine how long this will be. You can be a little more clever and apply the binomial theorem, but still it will be messy. So instead we are now going to see how we can do this much more quickly using whatever we have seen in this section. The trick is to first write the exponential form of this complex number, which turns out to be 2 times e to the power I pi divided by 6. Let me again remind you of something. Here you are allowed to write any one argument. You need not always write the principal argument. Whatever is convenient, you use that here. This part, however, is fixed because this is the modulus. And then you, in the next step, you write whatever we found today. That is, it's the 7th power of 2 times e to the power I times 7, and this argument they get multiplied. And then you note that 7 pi over 6 is pi over 6 plus pi. And in place of that, you can write this, because this is what we first saw today, right? This times this is e to the power I times pi over 6 plus pi. And this, we are writing it like this, 2 to the power 6 times 2, because there is a reason. If you look carefully, this part is again that root 3 plus I, that is why. Now the 6th power of 2 is 64, and this e to the power I pi is minus 1, because cos pi plus I sin pi. So you get minus 64 times root 3 plus I. Of course, you can understand that this example, this thing has been cherry picked to show that you can get it quite easily. Not every power can be found like this, but you get the point that sometimes the exponential form, along with its properties, they help us immensely in simplifying calculations involving complex numbers. So this section ends here. There are 2 more sections in this chapter. The next one involves roots of complex numbers that we will see, and in the next video on complex analysis, we are going to see that, as well as the next one, which treats regions in the complex plane. Then our first preliminary chapter will be over. After that, we can move on to the actual complex analysis, and we will start there with analytic functions.